introductions. Start recording.
Okay, great. Thank you. Okay. Good morning, everyone. We are pleased to have Professor Aleksandr Aravkin give a remote seminar. Professor Aravkin is Associate Professor of Applied Math at the University of Washington, where he also holds adjunct appointments in math, statistics, computer science, and health matrix sciences. Since 2019, he has served as the Director of Mathematical Sciences at the Institute of Health Metrics and Evaluation. Professor Aravkin has made influential contributions to optimization and has also developed new methods and software for solving emerging problems in global health. So let's welcome Professor Aravkin.
Thanks very much for having me. It's a pleasure to be here. Sorry I couldn't be there in person, but hopefully can visit you again in the future. I very much appreciate the remote option at this point in my life. It's good to see all of you. So let me give a talk, and then if you guys have any questions, I'll be happy to address. Let me share this and then go to this view, continue to share. And then just making sure, can everybody see the talk slides?
Yes, yes.
Great. Perfect. Sorry. Yeah, so this is a talk on an approach that we're developing for joint parametric and non-parametric estimation in the context of large-scale inference with heterogeneous data. So this is joint work with the math sciences team, including Pang Zhang, Alex Xu, Kelsey Mass, Nora Gilbertson, Samir Ali. So it's Chris Murray, the director of the Institute for Health Metrics and Evaluation, and many IHME collaborators. So one of the pieces has been published, and then you can get the full, all the full contributions from that paper. But I just wanted to emphasize that this work is based on a significant collaboration across different research teams. And so to start, I just wanted to give a brief introduction to the global burden of disease study, kind of the context in which this work takes place, and talk a little bit about what I mean by heterogeneous data, and then basically tell you about the approach to combine kind of classic bread and butter generalized linear models from statistics and like a second stage for kernel methods to get the estimates that we need. Briefly talking about computational considerations and other interesting things like variable selection that we need for ongoing projects, and kind of share some modeling results and illustrations, because this is all based on a kind of a pressing problem. So the nice thing about that is we have some results, so you can kind of see the model in action a little bit. Okay, so the global burden of disease is a multi-year study. I believe the first iteration was in 2010, which is kind of continues to be done by, I believe, the largest scientific collaboration in the world, with more than 20,000 collaborators. And the goal is to quantify years of life lost to and impacted by every disease. And the idea here is to get granular estimates. So we want to know how many years of life are lost by age and by location. The location set is becoming more granular, and we care about diseases that impact early neonatal, less than 1 week, late neonatal, less than 1 month, and many other age groups, since the diseases that affect different age groups change, and of course by sex as well. And we're also interested, of course, we're more interested in the current times, but we have data going back to 1950, so we're interested in producing these estimates for 75 years. So the task is to get a lot of these estimates at a very granular level if possible. And these estimates inform policy and can help people figure out which disease to focus on, which disease is becoming an emerging problem. And there's many other people working at the institute. Has about 500 researchers. So they handle a lot of other aspects, including forecasting, the insights, to see what might be coming, and a whole bunch of different related tasks. But one of the core problems is just understanding how many people died in this highly granular way and what was the cause of death. A lot of further estimates are based on obtaining these, and this is a harder problem than you might think. So this is the context in which we're working in. So in this talk, I'll focus on two aspects. The first aspect is trying to get estimates for all-cause mortality. So this is just total number or rates of death across these 75 years, 20 age groups, sex, and a location set. And also give you some updates on more detailed level work, which is also focusing on cause-specific mortality for GBD 2025. And the results for GBD 2023 have been published. So I'll give you a citation, and then hopefully by next year, we can get the cost-specific mortality estimates out as well. And these estimates have been produced regularly, just to be clear, but kind of the approach that I'm talking about to producing them is new. And so we'll be able to see a little bit in the differences between past and present estimates due to the model. So in order to do these, to make these estimates, we have some covariates to help us out. So IHME produces granular covariates that are, some of which are specific in these granularities by location and year and age. Not all are that specific. Some don't change over time, for example. So these can help produce the estimates and are particularly important when data is sparse and we're sort of facing an extrapolation problem to get estimates and locations with data. And the main challenge is that reliable age-specific mortality data is simply not available across these granularities. Some locations, for example, high income, have a lot more data than others. The United States has vital registration data, can essentially look at the mortality pattern by age group in the United States across time, but other places rely on other data sources. And so to get an approach that works well in kind of both regimes, the data sparse and the data dense, the overall theme here is to basically combine things that we know how to do well in a clever way. So combine classic statistical modeling with generalized linear models. It's like your parametric model that can do extrapolation in the sparse data regime with kernel regression that can fit data well in the data-rich regime to get reasonable fits in data sparse location and times, and good fits in data rich location, and basically seamless integration, since we want to be applying these things at scale and producing estimates in a systematic way. So I have an illustration, a little bit about the illustration for the data. So only 86 out of 204 national units have vital registration data, which is considered a gold standard data source. And even there, the vital registration data sometimes is limited by age granularity, with less data for older and younger groups. And so the remaining 114 countries that don't have vital registration data use alternative data sources, including complete birth histories and summary birth histories, which are typically only available for children and adolescents and may not be available for some portions of the time series sibling survival history data, which for adults can be highly uncertain. So the data can simply be quite noisy. You might see it in some of the plots, household death recall, and sample registration systems for India and China. So the data sources are heterogeneous and chunks of the data may not be available, particularly in places like the sub-Saharan region and for some of the earlier times. And so as an example illustration here, the top panel shows vital registration data time series. The x-axis is shared for the two plots. So this is data from 1950 to 2020. So you can see that in the top panel, the U.S. District of Columbia has a lot of vital registration data, and the kernel, all the kernel fit, which is the dark blue line, has to do is follow this data, and it produces a useful estimate and people are generally happy with it. In contrast, the bottom panel shows a sparse data example. So the X's represent data that have been outliered using expert considerations. And so the only data points that we have are the purple dots. And so we're missing the chunk of data from 1950 all the way to almost 2010. And so in this case, we only have 5 data points, and fitting that with a non-parametric model doesn't really make any sense. And so kind of a much more parsimonious model, like a classic GLM, that essentially provides a reasonable extrapolative fit is the best that we can do. And then kind of one of the tasks is just how do we, we don't want to have location-specific models because we do learn a lot from considering all the data and tasks together. So how do we design a system that allows us to do this systematically? So the idea, and this is a cartoon, just to get the high level, sort of a staged model where first we have the classic GLM, and then second, we have a second layer that does kernel regression. So the classic GLM model gets the rough idea using all data kind of down to the national level, but not proceeding to subnational. And that's kind of like this sheet lying on the couch. I mean, of course, if we're thinking about best fit, then the sheet would be going through the couch in some sense. But you see where I'm going with this. We can place the sheet on the couch, and that's like our first level approximation of a couch. Then kernel regression, when the data is available, is then the fitted sheet. It uses the predictions from the generalized linear model as an offset and uses more granular data and goes down to the subnational level and then improves fit for data-rich locations. That's the main idea. And just to review kind of the mathematics behind generalized linear models, generalized linear models combine likelihood estimation with a link function, typically a linear predictor to model outcomes. So for rates, since we're focusing on rates in this talk, the binomial likelihood is key. So the binomial likelihood you've probably seen before, and the link function is the xbit. And then we have our linear predictors AI. So the linear predictor AI transpose theta, I'm sorry, and then the features that inform the linear predictor are based on covariates as well as intercepts across some of these granularities. So in terms of covariates for all-cause mortality, just to make this more concrete, we use sociodemographic index, HIV mortality, since we're talking about death rates that can help, particularly in some locations. COVID-19 mortality, particularly in recent years, is really important. And then binary island covariate, whether a nation is an island, turns out to be surprisingly important. Like your outcomes relative to your neighbors can change quite a bit depending on whether you're an island or not. And then we have an aggregate summary exposure to risk variables that is kind of a IHME modeled covariate that includes everything that we know about kind of preventable things. And then to make the baseline model better, we also include location-specific intercepts and age-specific intercepts and incorporate smoothing. So that lets, for example, covariate multipliers vary by age group, since depending on the age, some of these things, HIV mortality may impact you differently depending on whether you're in the 30 to 50 group or in the neonatal group. So we allow for that flexibility, but we incorporate smoothing in order to borrow strength. On this tool, that would resulting tool that basically lets you specify the generalized linear model together with intercept and smoothing structure. There's a lot of specification there, so we provide that to our colleagues at IHME through the SPX mod Python package, and I've included a link to that. Okay, and so this is the kind of, so this is age and location varying coefficients that we might get when we analyze the all-cause mortality in a particular location. Like here, we're looking at Sierra Leone males, and so we have global intercept by age. So you can see that there's a different overall pattern in the global intercept that is reflective of the overall mortality rate. So this is global. This isn't specific to Sierra Leone. But when we get to the location intercept, this is the modifier by age of the total basically some intercept that is specific to Sierra Leone. And then we have covariate multipliers for the covariates I mentioned, HIV mortality, island, and then you can kind of see that is island can help decrease your mortality quite a bit, particularly for the age groups from 10 all the way to 60 or 80. So these are kinds of the covariate multiplier view that we can have, and then we can also kind of reason from that about how well the model is doing. And then in the SPX mod framework, we can use optimization techniques to basically help the model out. Since the data can be quite noisy, one challenge that we saw is that implausible dips can occur near the oldest age groups when there's sparse data. And so basically it says your mortality rate is increasing by the time you get to 95, but then suddenly people past 95 have, you know, a decreasing mortality rate, which is not biologically plausible. And as a result of the fact that in the older age groups, the data gets particularly wide and particularly noisy. And so then we can include monotonicity constraints using an optimization formulation in the SPX mod package. Another reason why we need a standalone package to do these kinds of generalized linear models. Even generalized linear models are classic bread and butter tools. We need these extra bells and whistles to help regularize the fit. Since if you present like an overall mortality view as mortality is decreasing past age 104, that will not be plausible in the community, and you know that it's kind of coming from noisy data. It's a pretty interesting aspect. And then following up on this, for the second stage, just review a Gaussian process with binomial likelihood. So you guys may be familiar with Gaussian processes. We can incorporate exactly the same likelihood that relates the observations to the data. So in contrast to the previous model here, for every point on the grid, we associate an unknown variable. So Fij is now, for every particular estimate that we're interested in, some of these we have observations Yij, but for others we may not, and these are simply not present in the likelihood. And then we incorporate a smoothing term where the smoothing term is controlled by a particular kernel, and the kernel encodes relational information. So there's no covariates in this particular formulation. It basically says that we're trying to keep the estimates Fij close to the observations Yij and relationally related to each other through a quadratic piece. And then there's different types of kernels which have different properties, how local they are, how smooth they are, and there's a whole set of modeling decisions and modeling skill that you need to incorporate kernel modeling into this kind of specific applications. For example, recently we've been looking at a tail attenuation kernel, since there's often less data in the tails for some of the sparse data sets. So we want kind of a non-standard kernel to try to attenuate fits for the far side, which is a very specific kind of need in this particular application. And it's kind of interesting to see how one can design kernels to do this. It's kind of a brief review of non-parametric kernel fitting. So the computational consideration here is that the vector of unknowns in the non-parametric case is a very high dimension, since we have 2 sexes, 75 years, 20 age groups, and 905 locations, which includes national and subnational data. So that gives us 2.7 million unknowns. So 2.7 million unknowns roughly means that that's your decision variable length, and you're solving a least squares problem with a 2.7 by 2.7 million system. That's pretty silly. But fortunately, there's a Kronecker factorization structure for the kernel that is present here. So when the particular grids across dimensions are uniform with respect to each other, for example, all locations are on the same year grid, and all years are on the same location grid, which helps us here since we have a very regular structured problem that we're working with. Then the covariance function can factorize, and then we have a Kronecker structure. So that helps us speed up things quite a bit. So in the all-cause mortality case, we also solve independently by sex and location. So we end up having 1,810 regression problems, each of size 1,500. So we can split up the problems by sex and location, and then we can also take advantage of the Kronecker structure to speed things up. So the entire global fit can run under an hour on the computational cluster, whereas previous methods could take up to 2 weeks. And so the rapid iteration is particularly important since then you can spot problems early. In fact, like the PDF generation to generate stacks of 1,810 PDFs with all the panels to review is the more computationally expensive than fitting the model, which is always a good sign. Okay, and finally, we combine these two models together using an offset. So in the first stage, we can fit a generalized linear model where we have a prediction based on a linear predictor with intercepts and covariate multipliers exactly as I described, and that gives us a prediction Pij hat for everybody. And then we use the Pij hat as an offset in the kernel fit. And so the idea is for locations without data points, when we do this, since there is no Yij corresponding to that location, there's nothing to move your fit from Pij hat. So you're going to be using the estimate from the first stage of the model. Whereas for data-rich locations, you are going to have data, and then the kernel is going to adapt from that offset and fit. And this provides a sort of seamless integration of the extrapolative, like zeroth order, first order view of the simple model to, more and more data, so you can have an entire holistic modeling framework for these heterogeneous data types. And then these stages are fit sequentially using the one-mod Python package that is basically flexible enough to allow for some custom decisions. For example, when we go from all cause to cause specific, we might make different decisions about which stages of the model are used when, and the one mod package helps to orchestrate those. So that's a lot of discussion. So I just show you a couple of examples. So here is Zimbabwe versus California. So Zimbabwe, the SPX mod is a dotted line. I know there's additional lines in the picture, but you could probably ignore those for now. So you can see that the dotted line and the dark blue line, which are the first stage fit and the second stage fit, are overlaying each other since there's no data available in Zimbabwe to push you off in order to adapt. Versus in California, the dotted line, the general pattern is quite a bit off of the detailed California data, and then the kernel model then just follows the vital registration gold standard data for California, starting from the dots. So this is like kind of the contrasting situations in the same model. And then Kreg fundamentally smooths. It's a smoother since you're putting in a least squares term guided by the relational relationships that you encode into the kernel. But basically, you can see that it's still able to follow sharp changes. Here in the District of Columbia, in ages 15 to 19, there's a peak in mortality that's driven by this data. So as long as the data is consistent, you can still follow the data and obtain those changes. So for this application, basically, is basically a summary of challenging and modeling features for the model size and model space using numerical linear algebra and kernel structure for the two models makes them quite efficient. For the heterogeneity problem, when we have data sparse and data rich regions, SPX mod, which is the first stage, provides covariate-based estimates, and Kreg fits better data when it's available. And then in terms of problem they called collinearity of covariates, the first stage model allows you to include constraints, which doesn't make things particularly too much more difficult. So we can deal with collinear covariates, deal with the age patterns in the noisy data regime, and then helps to ensure interpretability. So for example, the HIV mortality multiplier has to be greater than or equal to 0. So if it's collinear with others and the model wants to say, oh, HIV mortality will decrease total mortality. We can't let it since it's not interpretable. And if you try to extrapolate it for locations where you don't have data, you might have really counterintuitive results. Yeah, and then let me just kind of pause there. So I have a second extension, but maybe before the let me actually yeah, let me talk through another piece and then pause for questions. The first part before I go to cause-specific mortality. So one thing here is um, one challenge is how do we obtain uncertainty for the model fits? So we always have model-based uncertainty. If we solve a least squares problem, we can obtain uncertainty intervals using classic asymptotic results. But because we include a prior, the model-based uncertainty will deflate the uncertainty interval in the presence of smoothing. So a stronger prior you put on, the smaller your posterior uncertainty intervals will be because we'll scale them down. So we have a calibration stage that helps to improve coverage and then can be chosen a particular scale. So basically what we do with calibration is we know that when we include a smoothing prior, we're going to decrease posterior uncertainty interval width. So the coverage is going to be smaller than 95%. And so using the available data, we can basically come up with an inflation factor for the uncertainty so that weighted residuals have a variance of 1 given the data that is available. So we can't test this in real data because we don't know what ground truth is, but in simulation, calibrated 95% uncertainty intervals have approximately 95% coverage on truth. And so for data-rich locations where 90% or more of the time series have observations, we do location-specific calibration. And then otherwise, we do region-specific calibration. So this is an example that kind of shows the uncalibrated confidence interval produced by the model is in dark blue, and then the beige region shows the calibrated uncertainty, which ensures that at least for the observed data set, the Pearson residuals would have width 1. And then let me give you guys some results. So the comparison here is between estimates produced by the previous round of the global burden of disease in 2021, which used life tables, a method that I don't have time to explain. The current estimates are GBD 2023 and WPP, which is the World Population Prospect, basically estimates produced by the United Nations. So you can see the total deaths in millions by year. You can see that the GBD, the new model predicts slightly higher deaths in the early years and slightly lower deaths in the later years in this kind of global scale. And then particularly for sub-Saharan Africa, the pattern is a little bit stronger, and then we see even more differences between the model fits when we dig down to the specific age groups. So basically in the younger age groups for ages 5 to 9, 10 to 14, 15 to 19, 20 to 24, in these age groups, we can see that the estimates in the newer method using this joint kernel approach are noticeably higher for the younger groups than the previous estimate, and the opposite is true for the older groups. So there's this kind of switch that happens. But yeah, let me just stop there. That's the kind of fundamental impact on results from switching the different models. And in summary, we have a simpler and faster estimation process compared to life tables. And then we have improved ability to estimate in locations, years, and ages with limited data. And then the results of all of this is we see 50 to 100% higher mortality in ages 5 to 9 and 10 to 14, particularly in early years. And then in many countries, higher mortality in ages 15 to 19 and lower mortality rates in ages 50 plus. And so these results have been published in this year's Lancet study of all-cause mortality rates and life expectancies. Okay, so maybe pause here for any questions rather than running straight through the next application to cause-specific mortality.
So a quick question here. So when you choose the kernel regression model, is there a reason for choosing that? Because we know that that can be sensitive to the choice of the kernel itself, right?
Yes. So, well, I guess what would you do instead?
Well, I mean, there are a whole lot of other regression models. So my question is basically, have you compared different choices of models, like for example, support vector regression, or even using a MLP kind of regression, multi-layer perceptron, relative shallow neural network?
But I think in principle, you could have other choices of the second stage non-parametric model. So I guess the requisite features are that it should be non-parametric, since in the second step, so yeah, so a nonlinear SVM would work. Uh, the outcome here is continuous though. So you have to be non-parametric, and you would need to be able to use the same likelihood in order to make it compatible with a first stage model. Um, but other choices might be possible, subject to these two things. Uh, and the third thing is you need to be able to encode. I guess the particular feature of the kernel that we like, is it builds on modeling expertise from past years where we have strong relational priors in the data. So we know that there's a location hierarchy and mortality rates are similar to for locations in the same location hierarchy. So that relationship is easy to encode in the kernel. And then we know we have some smoothness relationship across age and across time. So having these three dimensions are pretty naturally encoded into the kernel. So if you were to consider alternatives, you would also want to make sure that you could use that information there as well.
I see. I see. Okay. Any other questions from the room?
Can you go back to the models and the models with the kernel? Yeah, for these models, yeah. So for these two, two stage, right? I wonder, especially for the second stage, I wonder if it's possible to incorporate this P into the decision variable, and also how to choose this lambda, right, in practice.
That's a really good question. So for the incorporation, so the two-stage model as well set up to be extended to become a one overarching model. So that's a place that we hope to get to. And what you could do is you could combine the two objectives together into a single overall model. So PIJ's XBit, that is already a part of the first model. So we could simply add the two things together and then balance out which is pushing to what. So that is something that we're interested in, but haven't tested because frankly, when you're doing these things at scale, having stage-wise processing works really well because you can vet each stage separately. So stage-wise is typically something we do first, but that's a really interesting suggestion. Then choosing lambda is difficult. So I think for all-cause mortality, we were tuning lambda manually. But for cause-specific mortality, we have a pre-processing step where we try to analyze different properties of the data, including measures of spread and coverage, and then use that pre-analysis to pick different decision variables, such as the lambda and also kernel parameters. There's definitely sort of more, you know, definitely optimization-based approaches to choosing parameters. But in practice, it helps to have a simple pre-processing recipe because again, it's more robust and can be vetted. So I guess to finish, so for the all-cause mortality, I think there's a lot of tuning of the lambda to work across all of these different locations in a reasonable way. And for when we scale this process to different causes, then we have a pre-analysis step that gives us defaults based on the data behavior in the specific locations.
Okay, yeah, I see. So does the choice, I think probably, right, the choice of lambda also affects the length of this confidence interval, right? You talk about it as a confidence interval, right?
That's exactly right.
They
So
cover that.
if you drive up the lambda, it will shrink the posterior confidence interval because you're putting a stronger prior. So the calibration is trying to make the final interval robust to that by computing an inflation factor. So it's a different general challenge in statistical models. And calibration is an idea that comes from atmospheric sciences, some of the weather prediction models, but we basically have incorporated it as a standard post-processing step.
Okay, I see. Thank you. Yeah.
Just to follow up with confidence interval question. So, have you thought about, the more principled kind of uncertain interval estimation, like conformal predictions?
Uh, yeah, could you repeat or maybe be more specific?
Yeah. So there's a line of work in machine learning that's called a conformal prediction, which is basically to try to inject like a more principled and guaranteed kind of confidence intervals. Have you thought about that?
I have not actually. If you could send me a reference on conformal prediction, that would be very interesting. You can see if I can take any motivation from that in future work. Yeah.
Yeah, so I think the benefit of that is that that's going to give some statistically guaranteed kind of intervals. Although yes, I mean there are some assumptions for that more to work. For example, your data has to be IID or some weaker version of IID like exchangeable. I'm not sure whether the data here will actually satisfy this kind of requirement because you talk about the heterogeneity in the data itself, right? So, but I think that may actually provide some more principled way of quantifying the uncertainty here.
Yeah, no, typically using something immediately out of the box doesn't work, but definitely the ideas, like once I understand the idea, we can see how to use it. So it's very grateful for the suggestion.
Okay.
Great. Great. And then let me give you a little bit more on kind of the current work. So when we move to cause-specific mortality, the problem gets harder. So this is a contrast between the two. So all-cause mortality, even though we're doing it in a highly granular way, it's still only one outcome, which is all-cause mortality. But for cause-specific mortality, we have 234 causes. So the scale up of the problem is significant. We're basically doing 234 analyses, which are analogous to the all-cause mortality analysis, and there's more specific considerations for the different causes. And one of the specific considerations is, while for all-cause mortality analysis, we had 5 covariates that we sort of have been using historically and must keep using, and they're predictive. We don't have a lot more choice going that far back in time. For cause-specific, we have many candidate covariates. We have a library of 300 or so covariates that IHME produces, and then research teams that model specific causes have an idea of which of the covariates are likely or believe they may be likely to impact the specific causes. We also have additional heterogeneity across causes. For example, causes with lots of data like heart disease and very little data like rare cancers, noisy data, and then causes that have a lot of observed deaths and few observed deaths. So these are all kind of challenges in going from all cause to cause specific. So there's some additional tools that I wanted to tell you about in the second half of the talk. Probably won't belabor that, so we have a little bit more time for discussion. The discussion was very helpful, but this is sort of the overall picture view now, where the last 2 stages of the processing, the SPX model and KREG stages, are exactly the same as in the all-cause mortality. But there's also a rover covariate selection stage, which is a variable selection tool that we're developing and currently analyzing. So I just wanted to tell you a little bit about that. So when we're figuring out which covariates to select and also judging model performance, we've been using the skill metric. So skill is something you're probably familiar with in the machine learning literature also. So skill is like a relative performance metric that requires a baseline model and a measure. So if we use root mean squared error as a common measure, then skill would be 1 minus the ratio of the root mean squared error of the model you're interested in divided by the root mean squared error for the baseline. And typically the baseline model that we use is simply an intercept for each age group. So just like age-specific averages of the mortality rate. That's something we want to compare to and see if we can do better than that, incorporating many different covariates. So higher skill is better, and a skill of 1 means root mean squared error of the new model is 0, which means we perfectly fit the data. So this can be used for both in sample and out of sample. So you shouldn't think necessarily, okay, if my skill is 1, that means I overfit, because your skill is high, overfit, because you could also measure skill for out of sample performance as well. Again, using out of sample performance of group intercepts as the comparison. 0 means you're as good as the baseline, because then these two things are equal, and you could easily go negative if the new model performs worse than the baseline model. And skill is something that is more comparable across causes, but in contrast to root mean squared error, because for example, if your cause has a lot of death, high rates, then root mean squared error is going to be correspondingly higher. And so if you just give a numerical value, you have to know a little bit more context to evaluate how it's doing or give some relative measure, and skill is one such relative measure. So that's just the background on skill. So the Rover covariate selection tool explores the covariate universe, or the coverse, using out of sample skill performance, basically. So the modeling teams input all their knowledge to us by giving us sets of candidate covariates for each cause, which are covariates that they think may be related to or have been related to in past literature, or they feel strongly about may be related to the outcome of interest. And then Rover traverses basically the tree of possible models, starting with the intercept-only model and adding additional covariates. And each time Rover is making a decision about whether to which covariate to keep and keep building, Rover uses out-of-sample skill. And Rover has been efficient and effective for us, and then is basically we find that it's competitive with Bayesian model averaging. And then Bayesian model averaging, the reason that we specifically focusing on this one is Bayesian model averaging. Originally, we're thinking a lot about inference aspects. And then Bayesian model averaging does both variable selection and provides inference, since it provides some posterior uncertainty intervals for the different covariates, if you're familiar with it. Also, there's been some recent survey work showing that Bayesian model averaging is quite competitive with other variable selection tools that we might consider. So I will show you just a little bit of a comparison. So this is a survey paper by Raftery et al., which compares Bayesian model averaging to a lot of other, sparse regularization techniques, including lasso, SCAD, elastic net that you may be familiar with, and finds that it does fairly well in terms of both getting the correct variables that were used to predict the mechanism, and then also including additional ways to measure what's happening with the uncertainty intervals. And then in our, I guess, comparisons with Bayesian model averaging, one of the main differences between Rover and Bayesian model averaging is Rover is basing all of the decisions by out of sample performance, which typically Bayesian model averaging and many tools only focus on in sample when they're evaluating it. So Rover uses out of sample, and as a result, we think is doing well. So we're currently analyzing that behavior now, but empirically, we have better sensitivity and specificity, particularly as the number of candidate covariates increases to 40, 50, which we see in some of our models. We see that Rover outperforms Bayesian model averaging in simulations. So that's our basically go-to tool for this piece. And this is an example of how we use kind of Rover in practice. So this is a particular cause called neonatal preterm birth. And then the plot shows the Rover sweep for both genders, male in blue and female in orange. since we do the analysis separately, and then basically Rover builds the entire tree by adding covariates one at a time using out-of-sample performance prediction. Out-of-sample skill is shown in the faded line, whereas in-sample skill is shown in the blue line. At some point, after doing the sweep, Rover then finds the variables that result in the largest out-of-sample skill across the set, and then it records those covariates, and those are used in downstream modeling. So in this particular case, there were 2 more covariates for males and females that were selected, and the covariates are different, which causes people have different reactions to this. Some people think, covariates should be the same by gender, and other people think, no, not only should they not be the same by gender, but in fact, the covariate universes for different genders should be different. And so for now, this is what we get. I think it's okay. So we get basically a resulting estimate of out of sample skill with the SPX model. So Rover is like a meta model built on SPX, and then we proceed with those covariates for further steps in the analysis. And so it's just like we did a study to see what the top most selected covariates were across the 231 causes. And I think this is super interesting because this is like, I've worked a lot in variable selection, and typically when we're thinking about variable selection, we're thinking about one outcome, or at least I was. So this is kind of a trip. So basically across these 231 different causes of death, which include injuries, diseases, communicable, non-communicable, this shows you out of like the 300 covariates, how many times a particular covariate was included in the covers by the modeler, and then how many times it was selected. So healthcare access and quality index, which is a covariate IHME uses, it's very powerful and predictive. It was included as a candidate in 202, and then used, actually selected 148 times, and on down through different smoking, alcohol, education covariates. And then some covariates were never used at all. So it's also very interesting. So maybe there's 100 or so covariates at the Institute are just not being selected for cause of death modeling, which says maybe you don't need to pay as much attention to those covariates when you're updating your covariates. So it's pretty fun. And then this is a plot of the resulting skill from the Rover model only. So you can kind of see basically here, we plot in-sample skill and out-of-sample skill. You can see that some causes are definitely more modelable than others. So for example, ischemic disease and hemolytic disease, all of these things have particularly high skill, and then other causes are more difficult because the data might be noisy. So it's very hard to beat your basically age group intercept, at least with a linear model. So the second stage is if the cause-specific mortality. The SPX model and the KREG model are exactly the same as for the all-cause mortality that I just described. And then to Xiaosong, to your question, this is the pre-analysis step. So there's different hyperparameters, decisions to make. So pattern lambdas for borrowing strength, and also some kernel parameters. And then we have a pre-analysis step to set those hyperparameters ahead of time. And then sometimes we modify these or the strategies as we learn more from the teams. The teams give us the data, and then we run it for the 231 causes. This is like very hard, detailed work that you have to do because they very much care about the results. And it's very hard to find like a one-size-fits-all approach. So scaling up hyperparameter selection, I don't know if this is necessarily a hard math problem or a hard practical problem, but it's very hard. So Peng Jiang developed the pre-analysis approach, and it's worked fairly well for us to set good defaults. Great. So I think we've seen these similar patterns so far. So I want to see what else I want to show you. Yeah, so this is an example in Japan. It was showing you kind of, again, the diarrheal disease death rates, in particular Japanese prefectures. you can see kind of in practice what happens with the SPX mod and K-reg fits. So you get a pattern, essentially, the shape of the pattern here is dictated by the patterns of the covariates across time. So this kind of, yeah, so we'll just stop there. And then from the baseline, from the prediction, then K-reg adapts to follow the data and the data-rich locations. And then the final skill that we get after applying, final in-sample skill that we get after applying GBD cause, some of them are quite high, close to 0.8. Remember, 1 is the absolute best thing ever. So IHD, COPD, which is chronic obstructive pulmonary disease, and diarrhea, lower respiratory infections, they're very modelable. And then others, including multiple sclerosis, is harder to get. But this is the distribution of skill versus using group intercepts to predict in sample now across all of the different causes. Great. So let me just do, you probably may not care too much about the specific improvements in the results, but one thing I wanted to highlight is, yeah, so yeah, so one thing that we've done is for certain causes, we've done a detailed numerical study looking at in-sample skill versus out-of-sample skill. So in order to have out-of-sample skill for the entire model, you have to decide ahead of time what to use for holdouts that are not used to train the model. So IHME has a history of working with holdouts. So rather than taking holdouts at random, which may not actually be representative of what's going on, IHME uses specific holdouts that kind of are aligned with the kinds of missingness patterns that we see in practice. So we use those holdouts to check, basically try to get realistic performance. So in these plots here, green dot represents a particular choice of model from the past using the previous state of the art, which just gives you a value for in-sample and out-of-sample skill. And then we do a parameter sweep for exactly the parameters that Zhao Song, because Zhao Song saw through to the end of my talk somehow, just asked a very good question very early on. You see the parameter sweep. So you see that we're sort of, this point is below the frontier that we're now able to get using different values of the parameters. And then we have to make some particular choice based on pre-analysis, hoping to end up somewhere between 4 and 3, lambda 0.1 and 1, basically on the degree of smoothing in order to achieve better performance. So ischemic heart disease, the reason I'm showing this is a very important cause. So essentially, to have face validity, we want to be able to beat performance of prior art in modeling ischemic heart disease, both in and out of sample. And lower respiratory infections is another important cause. And then the difference between prior art and the current frontier is more stark. And then for people who are not experts in machine learning like you guys, I think for them it's also surprising that there's a sharp drop off. So as you increase in sample skill, your out of sample skill drops precipitously, which we all know to be the overfitting problem. But I think intuitively, sometimes people who work in this space, they think like, okay, well, if you can have better fit to the data, that means you're doing great. So this plot really helps drive across home that there is this trade-off, and then you want to just be at some place along the frontier. So yeah, I guess currently we're working on the cause-specific mortality, and also analyzing statistical properties of the Rover variable selection method with Stefan Steinerberger, who's faculty in the math department. He's a great guy. And also working on a software paper for K-reg, the package is released. And then the reason one mod is called one mod is all of these ideas generalized to any quantity of interest that varies across multiple dimensions. So mortality is one example, but there's others across the institute. So there's kind of a lot of deployment of this kind of technology to be done, and then lots of interesting questions as well. So let me maybe stop there and see. Wait, I don't know why. Microsoft Power. Okay, let me just stop there for now. Thanks very much.
All right, thank you very much. Are there questions from the room? Yeah, go ahead.
Um, where do you see like in the future machine learning really like what do we see as future progress in healthcare with using machine learning? Like, where do you see as areas that will be of interest, you feel, in the next years?
I think it's a really great question. So first, just for a little bit of context, so a lot of the data here is population level data, rather than some of the other domains that I know you all are working with, where you have individual level data, and the population level data can be also quite sparse. So in this particular application, you see there's this need to do well when there is no data whatsoever, and it's not currently kind of that's not typically the norm in other areas as far as I'm aware. So I think um, yeah, I think one future direction that would be really nice is to be able to combine a lot of the population level estimates that are produced to sort of improve performance of individualized medicine and things like this. So if you know the distribution of disease, you know the distribution of comorbidities in particular locations, I think that may give you a pretty strong additional information or prior, as you will, for some of applications that people are building. And then, I mean, that's one direction that like sort of like these estimates can maybe inform in a kind of a rigorous and systematic way individualized applications. And just applying machine learning to this space is also a question I'm very much interested in. So we're often asked like how can we improve time series prediction using current models? And so far, it's been difficult. And one of the reasons that it's difficult is the data. This is like an N of one type of problem, right? We have locational relationships, but it's quite imperfect. We don't have volumes. On the one hand, we have a lot of data. On the other hand, the data is very specific to the place where it's happening. So it's like, how do you extract the meaning from the data? I would be very curious to see how basically machine learning can help in some of those tasks.
Thank you.
Others? People online? So I have a question about the robustness. So it seems that currently, you didn't do much there to, I mean, more explicit way of, handling robustness. So overall, how would you do this to make sure, the data is, the model fit is robust? Because, I think, when, data is very sparse, obviously, that, single outliers or few outliers that can significantly distort the model, especially for the part where your data is sparse.
Yeah, that's a really great question. So, okay, so I was really interested in outlier robustness in general, and then I wanted to just, so I'll get back to your question in a second. Just wanted to show you this burden of proof viz that I actually showed Rui when we met. Um, so let me just share screen for a second. So we have a dose response relationship work across different risk outcome pairs, and then if we look at dose response relationships, then all of the results have trimming, which is the methodology I was telling you during our meeting. So all the red points in these things are automatically outliered using the trimming concept. So basically, I just wanted to, so I'm very excited about outlier robustness. In this particular application now on the core mortality estimation, we've been kind of we haven't done this yet. And so one thing that happens is historically, outliering decisions are made by the data team, which also is aware of a lot of extra contextual information. including the veracity of the data sources and things like this. And so actually, one of the things that we've been doing is the opposite of outliering, or suggesting unoutliering decisions, which is we've been developing automated methods to detect data which had been outlier in the past for some particular reason, but actually fits more with the overall model to help teams reconsider those decisions, which they still may not because they have basically specific options. So I think but to answer your question, basically, we do have trimming capability in KREG. So it would definitely be a future feature development to use it, and then we could detect points that are least fittable. But you have to be very careful because some of the points that are least fittable could be the points that are the most informative, like the Lowen point in Africa in 1950 that you have, or something like this. So I think that would take a lot of thought and development. But I definitely take your point. An outliering point would have a lot of impact. And roughly speaking, my impression is all the data decisions, because people have location knowledge and data source knowledge, have been relying on experts to review and vet those data points. And just in the way that unoutliering, automatically detecting unoutliering decisions to consider, we could provide a list of potential outliering decisions to consider. And then to do that, probably use the trimming idea where to each data point, we associate a weight and we solve the joint optimization problem to decide who are the most likely to be outliers and help them to consider that. So I think that's a complete answer. But I'm so excited that you asked me about outliers, because that's definitely one of my favorite topics.
I see. All right. Do we have any last questions before we close? People online? All right. Thank you very much. And thanks to everybody attending us. Oh, we have a.
No, I'm just waving.
Great.
All right. Thank you very much. Thanks for spending time with us.
Great. Thanks for having me. It's been a pleasure. Thanks for all the discussion.
Thank you, Sasha, for the great and inspiring talk. So I hope we could collaborate in the future, in the near future. Yes, in terms of all means, grant the proposal, research papers or whatever. Yeah. So it would be great if we, could host your visit in person in the future. Yeah. Okay. Thank you so much.
All right. You guys all good now.
Take care. Okay.